Hello everybody, and welcome to example 4 on page 63 of the workbook here. In this video we're just going to look at part A. So let's read the instructions, see what this is asking us. So which of the following pairs of vector spaces are isomorphic? And for those that are isomorphic, we'd like to find an isomorphism, so a function that's linear and invertible. Okay, so the theorem that we just talked about makes the first part of this question relatively easy to answer. Okay, so theorem 2.19 said that we can check to see if two vector spaces are isomorphic by just comparing their dimensions and seeing if we get the same thing. Okay, so in part A here, we're simply asking, is the dimension of R4 the same as the dimension of M2 by 2 of R? And it is, because we know that the dimension of both of those vector spaces is 4. Okay, so that's our first comment here. So isomorphic because the dimension of R4 and the dimension of M2 by 2 of R are both 4. Okay, and remember M2 by 2 of R just represents a set of all 2 by 2 matrices with entries in R. Okay, so we've answered the first part of the question. What about the second sentence? So if for those that are, we want to find an isomorphism. Okay, so that means we need a function that goes from R4 to M2 by 2 of R that's linear and invertible. Okay, and generally the easiest way to go about that is to kind of think about nice bases for the two vector spaces. So think about the standard basis for R4. Okay, and the standard basis for M2 by 2 of R, we're going to kind of naturally pair those vectors up to form our function. So for example, the first basis vector for R4 looks like that, and we could kind of pair that up with the first basis vector for M2 by 2 of R and just keep doing that. Okay, I'm going to try to write small so that I don't run out of space here. 0, 1, 0, 0. Okay, and then 0, 0, 1, 0. That will correspond to, okay, and then finally 0, 0, 0, 1 is going to correspond to the matrix 0, 0, 0, 1. Kind of a natural way to pair up our elements. Okay, so can we use that above correspondence to build a function? So the above correspondence and linearity yield the following isomorphism. Okay, so we want to define a map now T that goes from R4 to M2 by 2 of R. We want to start by asking, where would an arbitrary 4 tuple get mapped? Okay, well, we can answer that question by sort of asking, how do we build ABCD as a linear combination of our 4 basis vectors? Well, let's sneak that into the top margin up here. Okay, so ABCD looks like A times our first vector plus B times our second vector, and so on. And so to figure out what goes over here on our output, just ask yourself, what would the corresponding matrix look like that gets built using those same coefficients? Well, it would look like this. Okay, and if you do that arithmetic, what you come up with is this matrix A, B, C, D. You might have been able to guess that without doing as much writing as we did here. Okay, but this function that we just wrote down has to be an isomorphism, okay, by kind of the construction, the linearity that we're using here. All right, so that's part A. To summarize, these vector spaces are isomorphic because the dimensions are the same, and then by kind of pairing standard basis elements, we arrived at this function as an isomorphism, a natural correspondence between the objects in our two vector spaces.